So now that you guys know where the long-run relative frequency probability is coming from, we can talk about the different rules for probabilities and formalize probability models. So to start, there's two main criteria for having a valid probability assignment. The first one is that if you have an event, that the probability of that event has to be between 0 and 1. It can be 0 and it can be 1, but it can't be negative and it can't be greater than 1. And that probably makes intuitive sense for you. The second criteria for probability assignments is that the sum of all possible events, those probabilities have to equal exactly 1. So that means that the set of all possible events, everything that possibly occurs, one of them has to actually occur. So you can think about a coin flip. The sample space is heads or tails. At least one of those has to occur. So the probability that you get a heads or a tails is exactly 1. So let's go through a problem really quick to see what probability assignments might violate this. So in this problem, we're looking at a plastic spinner. You know, from child's games, you might think of twisters as having 4 different colors in it. So red, yellow, green, and blue. And below this are different probability assignments. So this first probability assignment, assignment A, we can look to see whether or not it violates any of our criteria. So the first criteria is that all of the probabilities have to be between 0 and 1. And you can see that all the probabilities are between 0 and 1. So that's okay. And then the sum of these probabilities have to sum up to exactly 1 because these are all of the possible outcomes from spinning that plastic arrow. So when we add these up, what we'll see is these are exactly 1. And so because the entire sample space, that probability is exactly 1, that also means this probability assignment is valid. So probability assignment A is a valid probability assignment. The second probability assignment, assignment B, gives equal probability to each of the different colors. So all of those are between 0 and 1, so that makes it valid. And then when we sum up those 4 numbers, those 4 possible outcomes equal exactly 1, so the probability of getting a red, yellow, green, or blue color is exactly 1, and so this again is a valid probability assignment. C is also a valid probability assignment. What this spinner would look like is that it would be all red, there would be no other colors. But it's still valid because each of the probabilities are between 0 and 1, and again it's going to sum up to exactly 1, so that probability assignment is valid. Now D and E are a little bit different. You can see for probability assignment D, those have all probabilities that are between 0 and 1. But when we add these up, we're going to get something that's greater than 1. And so this entire sample space will be greater than 1. And so that cannot occur. So this is an invalid probability assignment. And if you use this probability assignment, you're going to get really strange numbers. The last probability assignment is probability E. And you can see that there's a negative probability here. There's also a probability that's greater than 1. And we said that violates our first condition, that probabilities of any event have to be between 0 and 1. And so this again is an invalid probability assignment. So those are the 2 important criteria for having a probability assignment. The next 3 rules that we're going to talk about are rules for dealing with probabilities and how you can get one probability from another. So the first rule is what's called the complement rule. And the complement rule lets you find something when you need to know the exact opposite. This rule is particularly useful when the problem you're looking at wants you to calculate at least 1. So the opposite of at least 1 is just none. And sometimes it's easier to calculate none. Let's say, for example, you flip a coin 3 times and you want to calculate the probability that at least one of them is heads. So that means the first one could be heads, or the second, or the third, or any combination of them. That's a lot to calculate. In fact, it's easier just to calculate the probability that none are heads because there's only one way to get no heads, getting all tails. And then use that to calculate the probability of at least one. So the complement rule says look at the opposite, subtract it from one, and you can get the at least one. So you're going to subtract the probability that you'd get none from one, and you would calculate the probability of at least one. So here's a problem to make that a little bit more clear. Suppose you want to calculate the probability that at least one card is read after you draw two cards with replacement. So it's kind of hard to calculate the probability of at least one because you have to calculate the probability that the first one is read or the second one is read or that they both could be read. So to make it easier, what we're going to do is we're going to calculate the opposite of at least one, which is none. So we're going to calculate the probability that none are read, subtract that from one, and that's going to give us the probability that at least one is read. So if none are read, that means they're both black cards. And the probability of getting one black card is just 1/2, because half of the deck, 26 cards, is black. And so we're going to do that for both black cards because we're drawing with replacement, and we're subtracting that probability from 1. So the probability that at least one card is read is 0.75. So again, this rule is really useful anytime we're looking at something that says at least one or some. That's a big indication that those words are pointing you towards using the complement rule. The next rule that we're going to look at is what's called the addition rule. And the addition rule says you can add two events anytime they're disjoint. So you have to be looking at the probability of one event or the second event, event B. So the word in the question should use the word or and not the word and. If it uses the word or, then you know you're dealing with addition. But simple addition is only appropriate when you're dealing with specifically disjoint events. So this simple addition only applies to specifically disjoint events. So let's talk a little bit about what that means. So disjoint events implies that they do not have the same outcomes or they can't occur at the same time. So for example, if you roll a dice, you can't get a 2 and a 3 at the same time. You can only get one of those. So those are what's called disjoint events. The same thing is true with a coin flip. You can't get a heads or a tails at the same time. Those again are disjoint events because they can't occur simultaneously. Let's look at a couple of problems to get at this concept of disjointness. Let's say you randomly select a person on the street to interview. Now, there's different characteristics about that person, and so we want to look at which of the following events are disjoint, meaning they can't occur at the same time. So this person that you're interviewing could potentially be black and female. Those can occur at the same time, so they are not disjoint. Same thing about being a Republican and female. Those are also not disjoint because they can occur at the same time. Same thing about being a female and being an athlete. Those can also occur at the same time. But being female and having a Y chromosome cannot. Females typically have just 2 X chromosomes. Y chromosomes are what designate a male instead of a female. And so this disjoint event would be events being female and having a Y chromosome. So back to the rule. The rule says if we have 2 disjoint events, meaning they cannot occur at the same time, and we want to know the probability that one or the other happens, we can simply add them up. So here's a great problem that gets at this. You draw one card from a deck of 52 cards. We want to know what's the probability you draw a queen or a king. Now these are 2 disjoint events because if you draw a card, it's either going to be a queen or a king. They can't happen at the same time. And so we can simply add them up. The probability that you would get a queen is 4 out of 52 because there's 4 queens in a deck. And the probability that you would get a king is 4 out of 52 as well. And so that last answer is how you would calculate the probability that you would get a queen or a king. And that probability is about 0.1538. So a pretty small probability that you would just draw a queen or a king. The last rule we're going to look at is what's called the multiplication rule. And the multiplication rule applies whenever you're looking at and between two events. So if the wording in your question uses the word and for two events, then that's signaling that you should use the multiplication rule. Now the multiplication rule here says that we can simply multiply two things together provided that they're independent events. So let's talk a little bit about what it means to have independent events. As I mentioned a little bit before, the independence of events depends upon the relationship between A and B. If the outcomes in A affect the outcomes in B, those are what's called dependent events. But if the outcomes in A do not affect the outcomes in B, they're independent. So for example, coin flips, they would be independent. So the outcome of a first coin flip is not going to affect the outcome of the 100th coin flip, or die rolls, or even sometimes card draws if you replace the card. So here's a problem that looks at independent events, a die roll and a coin flip, because the outcomes in the coin flip do not affect the outcomes in the die roll. It also uses the word and so that's how we know we can use the multiplication rule. The probability that you get a 5 is 1 out of 6, because there's only one way to get a 5 and 6 possible outcomes. We also want to include then the probability that you'd get a heads, and that's 1 out of 2 possible outcomes. So 1/6 times 1/2 is the answer, and that's going to be a probability of 0.08333. That's a real small probability for getting both a roll of a 5 and a heads. The two common mistakes when doing these types of problems is presented here. So the first mistake is multiplying probabilities that are not independent. When you multiply probabilities together that are dependent, you create lots of problems and create lots of biases and errors. And this is actually a pretty common problem that even pretty advanced statisticians still make. The second common mistake is confusing disjointness and independence. Those are two separate concepts. Independence says that the outcomes in one event do not affect the outcomes in a second event, whereas disjointness says they cannot occur at the same time. And so because they're different concepts, we use them in different ways. So that's a quick overview of the basic probability rules. Next, I'm going to go over a few pretty easy problems on how to apply these concepts of the addition, multiplication, and complement rule. And then the next set of lectures, we're going to go over how to make those rules more general so we can deal with non-disjoint event and dependent events.